In this second example with logistic regression, we'll be seeing how to fit a logistic regression model with what I call grouped data, right? So the previous example was with ungrouped data when data were recorded at the individual level. And this situation, we're going to be fitting what I call a logistic regression model with grouped data. So let's read in the data. It's in this those data set. And I'm going to attach it. And so again, as I always say, just a good thing to take a look at how the data are recorded for your particular data set. So notice how this is grouped, because this is basically from a chemical experiment where I believe insects were given a certain dosage of a chemical to see how many of them died. So the first group of insects were given a dose of 2.68. There were 31 of them and 10 of them died, right? So you don't have the information for each individual insect to see which one survived or not. You just knew that 31 of them got this amount of this dosage and 10 of them died. And then you had 30 insects who got this level of dosage and 17 of them died. So that's why I say this is group data. And when data are recorded in this way, the way in which we use R to fit a logistic regression model will be a little bit different. So now we know the number of in each dose and the number that died. So the next thing we have to calculate is the proportion for each dose, and that's going to be stored inside this thing, which I'm going to call prop, right? So it tells me, right, 32% died for the first dose, 56% died in the second dose. Another thing you can do with group data is to actually plot use a scatter plot of the the predictor, the log dose, versus the log odds based on the proportion, right? So the log odds is basically the log of the proportion divided by 1 minus the proportion. So I'm going to run this, and the idea being that if, right, this follows a straight line, then it tells us a logistic regression model is plausible. In this case, we notice it's not really a straight line relationship like over here. If this data point was like closer over here, then maybe. So now this looks a little questionable, right? And just bear that in mind as we carry on with the analysis. So we're going to fit a logistic regression model with the group data. We're going to use the GLM function. The response is going to be the proportion, and the predictor is the amount of dose, and family binomial. And in this case, we have to put this thing called weights, and that's the weights are going to be based on the sample size for each dosage, right? So that's where we put size for the weights. I'm going to run this and then produce the summary function. Use the summary function to see, right, if our coefficients are significantly different from 0. So that appears to be the case. Now, notice in that plot that we looked at, the plot of the sample log odds with the predictor, we noticed it wasn't a straight line. So we kind of think that kind of suggests to us that the logistic regression model probably may not fit our data well. So when your data, when you have group data, you could perform the Pearson chi-square and deviance goodness of fit test, right? So those tests can't be performed when you have ungrouped data. So let's see how we could do that. So the Pearson chi-square goodness of fit test, basically we just need the residuals from our GLM model using the Pearson type. So we're going to store all of these inside Pearson, and the test statistic is just going to be the sum of these squared Pearson residuals. So we can see what the test statistic is 28. So to find the goodness of fit test, the result, right, we're using this sum of the squared Pearson residuals. That's our test statistic. The degrees of freedom is going to be n. So n is the number of groups we have, which is 9, minus 2 because we have two coefficients, one for the intercept and one for the slope. So that's how we find the p-value associated with this Pearson's chi-square goodness of fit test. So the null hypothesis is saying that the data fits the model well. The null is saying that the model doesn't fit the data well. So in this case, we've rejected the null, which tells us that, right, the data doesn't fit the model well, which kind of goes hand in hand with what we saw with that plot, right, of the residuals. The plot of the log odds with the log dose. So let me just produce that plot again. Right, we say that if it's reasonable, then we expect this to look like a straight line. In this case, there's this data point, right? So it's not a straight line. So it's not surprising to see that we ended up rejecting the null, and we say, okay, right, our data doesn't support the model. The other thing we could do, right, is there's another goodness of fit test called the deviance goodness of fit test, which is based on the residual deviance. So you notice this residual deviance is pretty close to the
Pearson's chi-square test statistic, these two values will be asymptotically the same. So if you have a large sample size, these two should be the same. So again, I'm going to use that to run the goodness of fit test using the residual deviance. P-value pretty close, right? Again, the test statistics are pretty close, p-values are pretty close, they are asymptotically similar to one another, right? So in this case, we know with this data set that the goodness of fit test tells us, right, that our usual logistic regression model doesn't fit well, right, with this particular data set.